30.
Can I get some kind of extra credit for this?
Oh, no, put it back. No, you're on time, so much.
I'm 22 now.
You see the light on the desk?
There's way more traffic in here.
Oh, yeah, we have to get up at 5:30. So, what we got last time is that the expression for energy per unit volume call it U of the electromagnetic radiation in a cavity is simply 8 pi over c cubed frequency squared times average energy of an electromagnetic wave with frequency nu. So this is the average. Electromagnetic wave of frequency times delta nu, so energy per unit volume of waves with frequency in the range between nu and nu plus delta nu. And this is a thermal averaging. Which means electromagnetic radiation in equilibrium at temperature this whole factor here simply comes from counting the number of waves in the frequency range. It's actually 4 pi over c cubed, and 2 is for the two polarization states that the electromagnetic wave can have. Okay. Now, you know basically that Maxwell's equations describe nothing but a whole bunch of harmonic oscillators, right? Okay.
Not
You don't
quite
believe
clear yet.
No, I believe you.
We're willing to believe it.
That's
No,
next
but
chapter,
it's-
Nina.
No, it's easy. It's easy to see that. Okay, forget about sources. So we're talking about radiation only, and electric and magnetic fields satisfy what equation then? Yeah, wave equation. And what is a wave equation? But a collection of oscillators. That's it. I mean, we can go and, be anal about it and, derive every step, but the fact that they are harmonic, they are wave equation, that is a wave equation, this means there's a harmonic oscillator. So there is a kinetic energy term, which is basically this piece in the Abelian equation. That's a kinetic energy term. I mean, or kinetic energy contributes to this piece. Because if you have Newton's law, F equals ma, so some force, which you can say is kx, right? This is mass times the acceleration. So if you're looking actually at the changes in velocity, they're described by this, right? And this gives you rise to for the kinetic energy. This piece gives you rise to the potential energy, and the sum is constant. So this piece gives rise to kinetic energy, and then this piece, what is it? Okay, so it's this thing here. Do I have C in the right place? No, I don't.
G2DC.
This piece basically is the differential force, or it's the gradient of this acts like x, and so the gradient of a gradient, which is what the Laplacian is actually the force between the two neighbors. If you think in terms of a spring, it's called the spring is stretched by two particles on two ends. Of course, there are no particles, but it's just a matter of imagining how it works. So this piece gives rise to the potential energy. And the fact that you have magnetic field, well, they are not independent of each other, they tag along. So you don't need both of them to describe it. So, and then there are two polarizations, because it can either be this way or that way, or they can circulate polar. It doesn't really matter how you describe it, it's just a matter of truth-over basis. So this is a bunch of harmonic oscillators. And in thermal equilibrium, kinetic energy gives you 1/2 k Boltzmann T in classical physics, and the potential energy gives you this for the total of k Boltzmann T. So classical physics would tell you that this thermal average at a temperature T is independent of the frequency, and it's just equal to kB T. So in classical physics, then you would get a result that U is 8 pi over c cubed mu squared k Boltzmann T times delta mu. That's a classical physics result. And the total energy is then integral over all frequencies of u d mu. Well, of delta u times d mu. That's what it is. So this would be energy per unit frequency times d mu, and this would be proportional to integral from 0 to infinity mu squared d mu, which is infinite. So basically, classical physics will tell you that black body contains infinite amount of energy, which we know that's not the case. Also, classical physics gives you a result from here that this E total, if you look at it radiated per unit time, this is power. And if you divide this power by the area, then this is intensity. Is proportional to the temperature. When we know experimentally that intensity so what we do actually know is this, experimentally, E total not equal infinity, and intensity is proportional to the force power of the temperature, not to the first power temperature. This is known as the Stefan-Boltzmann law. It's been experimentally discovered by measurement. So classical physics totally screws up. Now, one important lesson to remember is that counting of the number of waves in a frequency range, this is actually basically nothing more than how you basically count the number of sound waves in a pipe, which creates a sound, or number of waves on a string, and so on. There is nothing quantum in that part. Planck, on the other hand, knew what the correct result for this or this should be. Why did he know? He knew the experimental results. So he actually had the curve which was measured experimentally. So for example, if you measure intensity as a function of frequency, this is experimental result which Planck was aware of, then the curve looks something like this. It wasn't symmetric, the tail on this side was different than the one on here, plus it started at 0. And there is also another law which was known, which was Wien's law, which says that this peak intensity occurs at a given temperature, something like roughly lambda times the temperature is a constant. So there was a place, there was actually a relationship between the location of the peak and the temperature that peak occurs. For example, for a blank body like a sun, the temperature turns out to be around 5,000 kelvins or so on a surface, and so that's why the sun is yellow, because it emits most of its energy at a yellow wavelength. And the reason why, for example, if you take an old-fashioned stove, which electrical stove in your kitchen, why when the coil is fully heated it's red? That's because the temperature at which that coil emits, which is probably about 1,000 or so degrees Kelvin, will correspond to the red light, and so on.
This, you said this works for like waves on a string. Does it end up with the same like 8 pi over C without the KBT? Is that
okay? You will get mu squared.
Yeah.
We will not get c cubed. We will get whatever is the speed of the wave.
Right. C.
And
C
whether you have
C.
8 or 4 pi depends on the number of polarization states that you have.
Okay.
So 8 is really 2 times 4. Well, this is the number of polarization states. So, Planck knew that something was wrong, and he figured out how to get the correct formula for this. So how did Planck do that? Well, he knew a little bit. There were, yeah, I guess he knew it. The first time when the first calculation he did was he just fitted. He fitted experimental result to a curve which he knew roughly what it should look like. He basically knew that this should be a combination of some exponential and some other function. So he was able to guess what the function is, he was able to fit it, and he got a result. The modern way to get this result is actually to consider statistical physics. And so in statistical physics, what you say, okay, so we have some energy, quantities that carry energy. We call it quantum modern in modern language. For Planck, that was just a wild hypothesis. And average energy in statistical physics is defined as sum over energy of E times e to the minus energy divided by k Boltzmann T, and the denominator is the same sum. Now the sum could be an integral or the sum depending whether these energies are discrete or not. So this is just a symbolic notation, but the key to doing statistical physics is to define the partition function.
Is it a moment function?
Huh?
That's a moment function, right?
Partition. This is an average. So you define the partition function, which is sum over the energies of E to the minus n. Beta E, where beta is just 1 over the K Boltzmann times the temperature. Okay. There is actually a normalization constant in a partition function, but it doesn't matter because it will cancel out. So you can just define it like this. And frequently we actually write this to be e to the minus beta f, where f is the free energy. This is one of the thermodynamic potentials, but it doesn't really matter. So, if you want to calculate the E average, consider the logarithm of the partition function. Which happens to be minus beta f. Now take the derivative of the logarithm, and the logarithm for me is a natural log. So take the derivative of the logarithm with respect to beta. So if you take the derivative of the logarithm with respect to beta, you get 1 over z, right? And then you have a derivative of z with respect to the beta. So if you look at the definition of the partition function, derivative with respect to the beta will drop energy from the exponent. And we'll drop a minus sign, so we stick a minus sign in front. This here is the same here. So we have the formula that average energy is minus d log c. I don't care to write it in terms of the free energy, it doesn't really matter. But this is the formula we use. I don't think Planck was the first one who used this kind of a derivation for it, but that's what works. So Planck made a wild assumption that at a given frequency, energy of the wave is going to be some constant times the frequency, times possibly an integer. See, Planck was a smart fellow, and the reason why he knew how to calculate, because roughly the formula looked like this, where x was some factor, and he knew that this is some kind of a, that possibly this could be a geometric series. So when he was contemplating and playing with expressions, he tried it. That worked. It worked because it kind of fell in line with this. So if you assume that this is the energy, some constant frequency times an integer, and that integer turns out to be, in quantum mechanics, the same integer which tells us which state it is. And so the harmonic oscillator which describes that particular wave at a given temperature would be in a particular state which is sufficiently hot on that tower of states that we have built for the harmonic oscillator. But let's see how this works. So all we need to do is to calculate this partition function, which is easy. So z is sum